Hello, I hope you're all having a good day, and today we're going to have a look at this question on the specific latent heat of vaporization of water. The basic idea is just going to use numbers to try calculate that, but the first part of the question is to do a label diagram, so I'm going to do an animation here. So the first part is to half fill a steam generator with water, and then once you've done that, you're going to put a funnel on it and put it on a hot plate. This is to heat it up and produce steam. Now this right here is a steam trap. The steam from the steam generator flows into it, and any steam which condenses into water is trapped at the bottom, but the steam which is still gaseous can flow up through it and then pass into the tube and thus into the cup. So all the steam goes through, but no condensed water does. So just the hot steam, which hasn't condensed yet, is heating up the water, giving it energy. So the maths. The basic idea is that the heat energy gained by the water plus the heat energy gained by the calorimeter, the container it's in, is equal to the heat lost by the steam condensing plus the heat lost by the hot water, which is cooling down to the final temperature. In this question, there is no calorimeter because it's a polystyrene cup. It is assumed to be a perfect insulator, but it would just be the same mcΔθ formula, which is the mass times the specific heat capacity times the change in temperature. ml is your mass times your specific latent heat of vaporization, which is the amount of energy the water needs to change from steam back into water. And then because it's now water, it's mcΔθ again. So then we're going to use the figures from the question to calculate the mass of the water, which is 83.4 grams. Yeah, I'm sorry about that. Then you've got the delta theta water is 19 Kelvin and the delta theta steam is 70 Kelvin, and then the mass of the steam is 2.6 grams. That's the final mass minus the initial mass, because then it's just a change in mass. So then using the mcΔθ equations we got earlier, you're going to convert those masses into kilograms, so you're going to use SI units and then just multiply it all out. So you only have one unknown, which is L, which is what we're looking for. So once you multiply that out, you want to move all your numbers to one side, have your L on the other side, then divide both sides by 0.0026, then you'll have L is equal to 2.25 times 10 to the 6. You need your units, joules per kilogram. That's because it's the amount of energy needed to change 1 kilogram by 1 degree Celsius. So the rest of the question was to state two assumptions about the polystyrene cup. The first is that it is a perfect insulator, i.e. no heat escapes, and second is that it has a low specific heat capacity, i.e. all the energy goes into the water, it gets none. The second part was how did each of these help improve the accuracy of the experiment. The first one, that the steam had been dried, that is that no hot water got into the cup, so it was only the steam that was heating up the water. No extra energy from the hot water was getting in. And the second, the water was initially cooled. That is because if it was already warm, it would already have energy that you wouldn't be able to measure. You wouldn't be able to differentiate from the energy that you measured at the very end. Thank you all so much for watching. If you have any comments, please do. If any suggestions, put them down below. Thank you very much.